Appreciate everybody coming out here, sacrificing a Saturday morning. I know my Saturdays are precious to me. I'm assuming they are for you as well. How many of you were at football games last night? Up late, out late, team win?
Our team played on Thursday night.
Okay. Well, actually, my team, not we played on Thursday night, but my son goes to a different high school and we had a game last night.
Okay.
So anyway, thank you for coming. I will be presenting, the first unit is kinematics. That's traditionally the first unit that you come to in AP Physics or pre-AP or any flavor of physics. Talks about motion, things moving, velocity, acceleration, that type of thing. Just to give an idea, obviously I'm not going to be able to learn everybody's names in the short time that we're here, but how many juniors are in here? Okay, so it's like juniors are on this side of the room. Is that purposeful or is that just a natural?
It happens.
It's natural. And so seniors are mostly over here. So juniors, you're seeing physics for the first time this year? And you jumped right into AP Physics 1. Seniors, as a junior, did you take like a pre-AP Physics or? No. How many of you are taking physics for the first time? Okay. How many are taking it for the second time? Maybe it's pre-AP or a general. So a few of you have been through pretty much all the curriculum. You're just seeing it now in with a different level of depth and different types of questioning. This is my 5th year teaching. I spent about 20 plus years doing software development in information technology, and went to grad school in my early 40s. Got a master's in secondary education, so this is the second career for me. But a lot of the skill sets of analytical thinking, problem solving, they apply to math, they apply to physics, software development. It's all very similar. Everybody has a packet now, correct? If you have any questions along the way, feel free to stop me, ask a question. I'm mostly going to be positioned up here. I've got my PowerPoint presented. I'll be using my Mobi device to work through problems, on the board. So I'll be going back and forth from PowerPoint mode to actually working problems out. Everybody in here has seen kinematics, so this is a review. I know when you get to work, power, and energy, a number of you maybe haven't started that unit yet, or you've just started it. I know at my school, we just started work, power, and energy this past week. So when you get to work, power, and energy, that will be with Mr. Lambert. That will be more of a teaching session than a review session. Not going to go into a whole lot of detail on this slide. Hopefully everybody is aware of the difference between a vector and a scalar. Vectors have two things. What are they?
Direction and magnitude.
Magnitude and direction. So 10 meters per second in this direction is different than 10 meters per second in that direction. The magnitude is the same, 10 meters per second, but if the direction is different, it is a different vector quantity. So velocity is a vector, and speed is a scalar. Speed is how far something traveled divided by how much time. Velocity is what is your displacement, how far are you from where you started. And the classic example of speed versus velocity is you're on a 400-meter track, you make one lap, how far did you run? 400 meters. How far are you from where you started? 0. So if you found your average velocity, your displacement is 0, so your velocity would be 0. Your speed, you take into account the fact that you ran all 400 meters. In general, unless there's a compelling reason to do otherwise, when you're dealing with something moving to the right, we make positive direction, to the left we make our negative direction, and then up we make positive, down we make negative if you're dealing with something moving in the vertical plane. So velocity, displacement over time, speed is distance over time. if you get a question about speed versus velocity, you may end up with something like this. You travel you have 4 meters to the right and 3 meters up. What is your distance? What distance did you travel? 7 meters, right? You traveled 4 plus 3, so your distance would be 7 meters. What is your displacement? Displacement absolutely would be 5 meters. 3, 4, 5 triangles you will see very frequently. So your displacement would be 5 meters. Excuse me, handwriting is not the best in the world, but so your speed and your velocity would be different. Your speed would be 7 meters divided by how long it took you. Your velocity would be 5 meters divided by how long it took. Now, if you just traveled in a straight line from here to here, your distance and your velocity, your distance and your displacement would be exactly the same. So your speed and your velocity would have the same magnitude. So that's the type of question you may get, just checking to see if you understand the difference between distance and displacement, speed versus velocity. For the most part, in kinematics, you're going to be dealing with velocity. You're going to be dealing with vector quantities. Have you seen diagrams like this before? Once. These are, if you think of strobe lights, there's a strobe light, the flashlight comes on and then turns off, and the strobes are going at predictable intervals, every 1/10 of a second, every 2 seconds, some constant frequency. Imagine that an object is moving and there's a strobe light shining on, flashing, turning off, flashing, turning off. You see that object at distinct points in time. When it's dark, you don't see what's happening. So that's what these indicate. And you might get some questions asking what's going on with this particle right here? What's the spacing of? They're the same. So that would be an indication of something moving at a constant velocity. What's the difference between A and B? Which one is going slower? B. Yeah, B would be slower. Because if, say we take our flashes every second, in 1 second, or in 2 seconds, particle A has moved this far, particle B has, it's not moving as fast, and so its images would be closer together. What about C? What is particle C doing? It's accelerating, right, because every flash, it's progressively moving further and further, and then E looks like it's doing what? It's still accelerating, but it's slowing down. It would have a negative acceleration. So, looking at question 1, when you get a question like this, pick up on, say look at velocity first. What do we know about the velocity? Is it constant? Which way is it moving, right or left? Yeah, it's moving to the left, so that means it's got a negative velocity. And what's happening to the dots? Are they getting further apart or closer together? Closer together. So what is it doing? Just slowing down. So it has negative velocity and it's slowing down. So what's the relationship between velocity and acceleration in terms of something that's speeding up or slowing down? Well, acceleration is a change of velocity. If I'm traveling, say, to the right, I have a positive velocity. If I'm speeding up, then what direction is my acceleration? Positive velocity, positive acceleration means I'm speeding up. But what if I'm traveling in this direction and I hit the brakes? I'm slowing down. What direction is my acceleration then? Negative. So positive velocity, negative acceleration means I'm slowing down. If you have, the rule of thumb here is if velocity and acceleration have the same sign, that means you're speeding up. If velocity and acceleration have opposite signs, that means you're slowing down. So if you're speeding up, you can have negative velocity, negative acceleration. What's a classic example of negative velocity, negative acceleration? Something in free fall. Acceleration due to gravity is always down in the negative direction. And if something's in free fall, its velocity is negative. So negative and negative, it's speeding up. What if I toss something in the air and it's on its way up? What direction is its velocity? Positive. Positive velocity, negative acceleration. On the way up, it's slowing down. But then on the way down, it's speeding up. Common misconception is, oh, negative velocity means I'm slowing down. Or, excuse me, negative acceleration means I'm slowing down. And not necessarily. If your velocity and acceleration have opposite signs, you're slowing down. It's positive, negative, or negative, positive. So what's the answer to this one? See, negative velocity and positive acceleration. Because pick up on the velocity, it's moving to the left. So that means you have negative velocity and it's slowing down. Acceleration is, it's easy to see that it's accelerating, but the sign of the acceleration is not readily apparent unless you know that key rule of thumb. The signs are different. Slow it down. So negative velocity, positive acceleration. Motion graphs. Students always seem to think, oh, well, it's reading a graph. It's easy, right? How many of you have maybe struggled a little bit with motion graphs? One or two of you. Everybody else has them down cold. Let me give you a technique that I share with my students. You've got three types of motion graphs. You've got, a little bit bigger. And I like to stack them vertically like this. So I've got displacement versus time, velocity versus time, and acceleration versus time. And it doesn't matter what the graphs look like, but I'll just draw something like this. What are our units for displacement? Meters, right? Where is something? How far has something traveled? The units are meters, and time we measure in seconds. What are our units for velocity? Meters per second. And time, again, is in seconds. And for acceleration, units are meters per second squared. That's something that when I was taking physics in high school, I was like, meters per second squared, what does that mean? Then I heard at some point, well, it's meters per second per second. How many meters per second of velocity is changing per second of time? So but meters per second is the unit equivalent of meters per second squared. And then obviously time, we still have measured in seconds. Anytime you see a graph, two possible things may be of critical interest to you. One is the slope and one is the area. So on a AP test or exam or quiz, anytime you see a graph, whether it be a force versus distance graph, displacement versus time, velocity versus time, ask yourself, does the slope mean anything? How do you find the slope of a straight line? The what over the what? Rise over the run. So there's a reason that I put the units in here. If we look at the displacement graph, slope, focus on the units. The rise, what is the unit for the rise? Meters. So we end up with meters, and the run we measure in seconds. Meters per second. Ask yourself, does that sound like anything that I've seen before that's useful? Velocity, absolutely. So the slope of the displacement graph gives you velocity. So even if you can't remember that fact, everybody in here from math class knows rise over run. So rise over run, meters over seconds, meters per second. Oh yeah, the slope of the displacement gives me velocity. So anytime you see a displacement graph, you can substitute the word slope for velocity. This has a positive, negative, or zero slope. Positive slope, therefore it has a positive velocity. If you had a zero slope, it was zero velocity. If you have a negative slope, negative velocity. Simple as that. For a velocity graph, rise over run, I end up with meters per second for my rise over seconds. Meters per second, or meters per second squared. Does that sound useful? Yeah, sounds like acceleration. So the slope of velocity graph gives you acceleration. So if I have, again with velocity graph, if I have a positive slope, just substitute the word acceleration, it gives me a positive acceleration. If I have a zero slope, constant velocity means zero acceleration. Negative slope, negative acceleration. And if we look at the acceleration graph, the slope is meters per second squared per second, which is meters per second cubed. That's something that we've seen before. There is actually a term for it called jerk. It's the rate of change of acceleration, meters per second cubed. Any of you in AP calculus, AP we've seen a few of you, so you know about the slope, taking derivative of a graph. So meters per second cubed, it means something to somebody. It's called jerk. So we go from displacement, velocity, acceleration, jerk. The rate of change of jerk, this is just a little bit of trivia for you, snap. The rate of change of snap is crackle. Can you guess what the third one is? Pop. Exactly. So it goes meters per second cubed, meters per second to the fourth, to the fifth, to the sixth. I think it goes jerk, snap, crackle, pop, lock, and drop. I did not make that up. You can always get into lock and drop or drop and lock. I give it the last two names. So this is true not just for displacement or motion graphs. This is true for any graph. Ask yourself, is the slope useful? The other thing that may be useful is the area. So say I take some rectangular area of this acceleration graph. We all know how to find the area of a rectangle or a triangle, right? Rectangle is easy. It's length times width, or base times height. So if we look at the area, again, let's look at the units. If I take meters per second squared times seconds, what do I end up with? Meters per second. Well, meters per second, that sounds an awful lot like velocity. So if I have an acceleration graph, I look at the area under the graph. That will give me how much velocity was gained or lost during that particular acceleration. And for my velocity graph, and again, it doesn't matter if it's a triangle or a rectangle, you can all figure that out just by looking at the graph. But if I have an area under a velocity graph, I end up with meters per second times seconds. What do I end up with? Meters. So the area under my velocity graph gives me displacement. Notice the trend. The slope gives me the graph below it. The area gives me the graph above it. The area under a displacement graph is going to end up being meters times seconds, a meter second. Is there a graph above here? So the slope may or may not mean something. The slope of the acceleration graph doesn't, we don't care about. The area may or may not mean something. The area under a displacement versus time graph, we don't care about. But the velocity graph is the more interesting of the three because the slope and the area both mean something. So that's the more likely graph that you would see on a motion graph problem. So position versus time graph, what's happening to the slope of this graph? As I go from A to B, is the slope getting steeper or is it approaching zero? So if my slope is approaching zero, what does that mean my velocity is doing? Approaching zero as well. The position versus time graph, the concavity means something. And let me show you the four possible types of concavity that you can encounter in a displacement versus time graph. For this type of curve right here, any point along this curve, my slope is going to be what? Positive or negative? Positive, sure. So the slope to the tangent line, let me draw that a little bit. The slope to the tangent line is positive, so that's going to give me a positive velocity. What is the slope of a tangent line on this type of section?
Down. Negative.
Down or negative. So I have a negative velocity here. Slope over here is again going to be positive. Positive velocity and negative velocity. So on the displacement graph, look at the slope, and if you have a curved line, look at the slope of the tangent line. Now let's look at what this object is doing. It has a positive velocity, but what is happening to the slope? What is the slope going to be right here? Zero. So it has a positive velocity, and it's slowing down. If something is slowing down, what's the sign of the acceleration going to be? Negative. So this is positive velocity, negative acceleration. This has negative velocity, and it looks like it's getting more and more negative. The slope is getting steeper and steeper and steeper. So it has a negative velocity, and it's speeding up in the negative direction. Again, negative acceleration. So notice the top two curves here have negative acceleration. The top of this, and in calculus, we refer to this as concavity. The top is concave down, so that means that you have a negative acceleration. You can probably guess what a concave up is. It's going to have acceleration. Yeah, positive acceleration. So when you're looking at a displacement graph, this is probably the most difficult concept to draw out of motion graphs, is what is the acceleration from a displacement graph? Because you have to look at not just the slope and not the area, but the concavity. Because you're looking at the characteristics of two graphs down, going from meters to meters per second squared. Questions so far? Look at you were given each of these scenarios. What's happening to the speed of each object if you have positive velocity, positive acceleration? Increasing. Positive velocity, negative acceleration. Decreasing. Sure, the signs are different. Negative velocity, negative acceleration. Increasing. Because you have the same sign. Positive velocity, negative acceleration. The signs are opposite. Again, it's decreasing. And you could relay each of these back to the previous slide. Here, you're decreasing because your slope is approaching zero, so your velocity is approaching zero. Here, you're decreasing because your slope again is approaching zero, so your velocity is approaching zero. Here and here, you have the same signs, so the speed is increasing. It's either getting more and more positive, or it's getting more and more negative. So we touched on the velocity versus time graph already. Slope is the average acceleration. You have a curved line, which you will seldom have on a velocity graph, because that would mean you have a changing acceleration. Usually we deal with constant acceleration. But the area under the curve is your displacement. So tell me what's happening at this first, from 0 to 3 seconds. What kind of graph is this? Velocity graph. And I'm going from what velocity to what velocity? 4 to 16. So velocity is increasing. Have a positive velocity and a positive slope. So that means I have a positive acceleration. Positive slope gives a positive acceleration. So that means that I'm speeding up. What about from 3 to 6 seconds? Describe what's going on with this object.
Constant velocity.
Constant velocity. Zero slope, zero acceleration. You have a constant velocity, and that constant velocity is 16 meters per second. And then from 6 to 8 seconds, slowing down. Negative slope, negative acceleration. One of the more common mistakes that I see students make is you see a graph like this and you don't pay attention to what type of graph it is. So if you see a graph, the very first thing you need to ask yourself is what kind of graph is it? Because if this was a displacement versus time graph, from 3 to 6 seconds, the displacement is not changing. It has a zero slope. That means it has a zero velocity. So some of you will be tempted to say, what's it doing during this section? Oh, well, it's not moving. So you take this exact same shape of graph, but it's not a velocity graph. It's a displacement graph, and that would be a true statement. But with the velocity graph, that means it's constant velocity. Y'all have this problem in your classroom. Can you read it? It's a little bit of a fuzzy. All right, so we've got some velocity versus time graphs for boats traveling along the straight and narrow channel. Scales on both axes are the same for all of these graphs. Each graph point is marked with a dot. So the question says, write the magnitude of the acceleration of the boat at the point indicated. So we're looking for the acceleration here, 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 and here. So magnitude means the absolute value. So you don't care if the acceleration is positive or negative, you just care what the numeric value is. And you ask yourself, how do you get acceleration from a velocity graph? Slope. So ranking them from greatest to least. Which one or more of these graphs has the greatest slope? The horizontal line has what kind of slope? 0. The more vertical a line gets, the greater the slope. So visually looking at these, which one or more have the greatest steepest slope? C and D. And if you wanted, you could actually figure out using the grid marks. Looks like the rise over the run, the rise from here to here would be 1, 2, 3, 4. The run would be 3, so it'd be a 4/3 slope. But on a problem like this, typically they're not going to give you something that's just slightly different. They'll make them visually distinct enough. So the greatest is going to be C and D. So we got that one and that one eliminated. What's the next greatest slope? B and A. Sure, B and A are the same. And it looks like this rise is 1 and the run is 2. This rise is 1 and the run is 2. And so we've eliminated B and A. So what's left? E and F. Positive slope, negative slope, that I don't care about positive or negative, I just care about the magnitude. And pretty sure that E and F have the same slope as well. So it turns out, it asks about the acceleration at that given point. It's the same acceleration everywhere because you have a straight line. A straight line graph, the slope doesn't change. So not a terrible problem if you committed memory that, oh, well, to get acceleration from a velocity graph, all I got to do is look at the slope.